All right, guys, and into the second half of our notes in 11.1. Now we start talking about the two big concepts right here at the beginning of chapter 11, permutations and combinations. So you may have heard these words at some point throughout the year. Combination certainly is a word you hear a lot, but let's get into what they mean. A permutation is defined as the following: an arrangement of objects in which order matters. Guys, those are the two really important words right here. And that means that a different ordering of the things that you have chosen creates a different outcome. So that's kind of what this little statement in green says right here. If we were to shuffle the order around, we end up with something that is substantially and significantly different than what we started with just a moment ago. So in just a second, we'll give you guys some examples of permutations. They're not that hard to come up with, but there's a formula here for permutations we need to have down. The number of possible permutations you could make when you select R objects, that just being some number, from a pool of n candidates. Well, first of all is just the notation right here. NPR, guys. The capital P in the middle stands for permutations, and N is the number of candidates, how many you're choosing from. R is the number of objects you are actually going to select. And the formula for this then is, here's some of the factorials we just talked about earlier in this section, n factorial divided by the quantity n minus r factorial. Now that's the formula. Honestly though, guys, your calculator will do this for you. I'll show you how in just a second. And I would think that in just about every one of these permutation problems you're going to see on homework or on a test, you're going to have your calculator there with you. So let's see it in action here, guys. All right. First example, you need to select a president, a vice president, and a secretary from a group of 10 students there in your class. In how many unique ways can this be done? So the first question you guys are going to want to ask yourself on your homework here, or a test question, is, when I'm making this selection right here, does the order matter? Is it a combination or a permutation? And we'll get into combinations in just a second. And in this example, because the three positions you're selecting people for, president, vice president, and then secretary, have different roles because they're unique positions, yes, the order there matters. Okay, if you were to choose you to be the president and then a friend to be the secretary, that's one way it could be. But we could flip that around a little bit and then make your friend president and you being the secretary, and that would be a different arrangement. The key here really is that word unique. So this is a permutation problem. So we're going to put a capital P right here. And the number in front of the P is the number of candidates you're drawing from. This is a group of 10 students that we're selecting from. So our N number here is going to be 10. And out of those 10 students, we need to choose one president, one VP, and one secretary. We need to choose 3 of those people in order to be appointed to these positions right here. So if we were going to do this by hand, that formula here is n factorial, which is 10 factorial, got it, over n minus r, 10 minus 3 factorial. And we could do this, it's actually not as hard as you might think to do on the calculator right here, but here's what I really wanted to tell you guys. Your calculator has the permutation formula built in. So what you guys are going to do here, it's a good idea to get in the habit of putting in the 10 first. So we're going to type that. All right. So I'm doing this on my 84 here, 10. And then what we're going to do is go once again to the alpha and then the F2 button right there, just like we were doing for factorials a second ago. So alpha, F2, and now, if you guys are looking at what I'm looking at, if I now hit number 7, all right, that opens up then the permutation thing. And the 10 that I typed in before now gets put in that spot. Then you're just going to type in a 3 right after that to fill in that R button, and then you can hit enter at the end of all that. And when you do that, guys, I got an answer here, hopefully the same one you got, of 720. So there are, well, that's a lot. There are 720 different ways we could select 3 people from our class of 10 to fill these 3 unique positions. Without a calculator, nobody cares, but this would have been 10 times 9 times 8 times 7 times blah, blah, blah. And on the bottom, 10 minus 3 is 7. That's 7 factorials, so 7 times blah, blah, blah. And all of this cancels out with that, just leaving you with 10 times 9 times 8. 9 times 8 is 72 times 10 gets you 720. So it's not as crazy as you guys might think to try to evaluate some of these by hand, but I'll stand by what I said. You'll be able to use your calculator here, and if you know how to use your calculator properly, you can just type that in and then get that answer of 720 directly without having to show any of this work or certainly any of that work. Okay, so that's one example of a permutation problem. Here's another one. Let's do some spelling. How many unique 5-letter words, and I put words in quotes here, guys, because they're not really going to be words, can be formed by rearranging the letters of the word Idaho? Okay, well, Idaho, those of you who are good at spelling, 1, 2, 3, 4, 5, has 5 letters right here. And out of the 5 letters in Idaho, the I, D, A, H, and O, we're going to select all 5 of them in order to make a new word. So, the arrangement of letters in a word here is important. And the example I always think about is if you have a little kid who's writing a letter to Santa, make sure they don't actually goof that up and write that letter to Satan instead. Same 5 letters. S, A, N, T, and another A, but the order matters, and it can pretty drastically change the meaning of the word right there. So, what's going on, guys? It's a permutation because the order matters. There are 5 letters in the word Idaho, and we are going to choose 5 of them. Oh, okay, so 5P5. So again, going to my TI-84, I would type the 5 in first, and then I would hit alpha, F2, and then number 7. Then I'll type in the second 5 and hit enter, and I ended up with 120 different words, quote-unquote words, that we could make by rearranging the letters, or the order of the letters, in Idaho. I mean, just to name a few, you could reverse things and get O-H-A-D-I, gotcha. You could switch the consonants and get I-H-A-D-O, or you could just get totally random here and go D-I-A-O. O-H. That's just what? 1, 2, 3, 4 of them now, but there's a grand total of 120. Some people like to solve this problem a totally different way. They like to go back to that problem we did a while ago when you were putting friends in your car and just think about how many options we have for each of the choices that need to get made. If these are my 5 letters, if you think about playing Scrabble, and I go to draw the first letter, I've got 5 tiles I could choose from. But then I can't use that first one again. So now I've got 4 options for the second letter, then 3, then 2, then 1, and sure enough, guys, we talked about this a while ago too, 5 factorial right there is equal to 120. So both of these are perfectly valid ways of solving this one. But I like that permutation method now because something interesting happens when we try the same trick with Ohio. Okay? Now, for example, I could take Ohio right here, which obviously there's one way we could write it there, and what would happen if I were to write it backwards? O-I-H-O. All right, there's another one right there. But the interesting thing is, what now happens if I switched just the first letter and the last letter? If these two traded places, I'd get O-I-H-O again. That is the same word, quote-unquote word, twice. The reason that this Ohio problem is a little bit more interesting than the Idaho problem we had just a second ago is that in Idaho, all 5 letters were unique. There was no repetition among them. But with Ohio, we've got the same letter being used twice. So I'm going to show you guys the fast way to do this one. There are 4 letters in Ohio, so we would begin by taking 4 factorial, but then you divide that now by the number of repeated letters that you have. There are 2 O's right here, so we would put a 2 factorial down here on the bottom. 4 factorial is 24, 2 factorial is 2. There are only 12 unique words, quote-unquote words, that we could make from those letters right there. And I wonder how long it would take me to list all of them out. Let me see here, guys. Let's see. I could do O, H, and then I could do O-I. All right. I could do O-O-H-I. I could do O-O-I-H. All right. Gotcha. I could do, let's start with an H now. I could go H-O-O-I, H-O-I-O, H I-O-O. 3 different places that I could be. So where am I at there? That's 3. That would make, that's 6, 7, 8. I haven't started any words with an I yet. So I could go I-H-O-O. I could go I-O-H-O. I could go I-O-O-H. So where was I? 3, 6, 9, 10, 11. Oh, shoot, and there's one that I'm missing. O-O-O. It's got to be hiding there somewhere, guys. Where's it at? Did I end one with an I-H-O-O? Yeah, I did that. I'm missing one of them right here. Well, I don't want to dwell on this for too long. There's 12. I'll come back and find that other one later. All right, here's a fun one. I ran out of cool states right here. I wanted to do banana. Same basic concept. 6 letters in the word banana. So we would start here with a 6 factorial up on top. But now this one is interesting because we have a lot of things repeated. We have 1, 2, 3 A's. So that means we've got to put a 3 factorial down there on the bottom. However, we also have 2 N's. That puts another 2 factorial down on the bottom there as well. So that 6 factorial, guys, would be, well, actually, the 6 factorial and the 3 factorial would leave us with a 6 times 5 times a 4. The 3 times 2 times, well, let me go ahead and write it. The 3 times 2 times 1 here would cancel out with the 3 times 2 times 1 from the 3 factorial. Then there's still a 2 times 1 down there on the bottom from the 2 factorial. That's a 30 times 4 is a 120 over 2. We would end up with 60 different words, unique words, we could make by rearranging banana. So those are all examples, guys, of what permutations look like. So anytime you're spelling a word, anytime you're dialing in your locker, anytime you're writing your phone number or an email address to somebody, the order in which you use those numbers or those letters matters. If you dial somebody's phone number, but you goof up a 5 and a 9, and instead you put 9 and 5, even though the digits are correct, they're not in the right order. It alters the outcome, and that's what we mean by a permutation. Now, all of that is in stark contrast to the last thing we're going to talk about here, which is a combination. And a combination is an arrangement of objects in which order does not matter. That means that if we make a different ordering, it does not change the outcome. So here's kind of the quick takeaway for a combination. A different order doesn't change things, and it's still the same combination. So we have a formula here for combinations that's really, really similar to the formula we had for permutations, except that it also has this extra r factorial down there in the denominator. Other than that, the two formulas are the same. Now, what I'm hoping you guys can realize pretty quickly, by putting an additional factor of r factorial, which could conceivably be a pretty big number, by putting that factor in the denominator, it makes the denominator of this formula bigger than the denominator of the permutation formula that we talked about before. But if the denominator of your fraction gets bigger, that means that the overall value of the fraction is getting smaller. So the number of combinations will just about always be smaller than the number of permutations that you could have. Now, for some reason, well, I get why, we'll explain it in a second here, people have a harder time coming up with examples of combinations than of permutations. As we said, phone numbers, email addresses, spelling words, those are all cases in which order matters, so those are permutations. But how about this example, which is a little bit similar to the president, vice president, secretary example we did just a second ago. But in that previous problem, they were all getting appointed to unique positions. The president's role was different from the vice president, which was different from the secretary. Now, in this problem, we're just appointing delegates. And it doesn't matter who's who. It doesn't matter if I pick you first and then your BFF second, or if I pick your BFF first and then you second. You're still delegates to this same thing that you're going to. So this would be an example of a combination, everybody. Once again, N is the larger number, the pool of candidates we're choosing from, and in this case we said there's 8 people to choose from. R, the smaller number, is the number of people we are going to select, which is going to be 3 here. So again here, guys, your calculator will do this work for you. Let me walk you through it. Probably a good idea to put the 8 in first, so I'll go ahead and type that in. And then just like before, you are going to hit second, and then I did that wrong again. You're going to hit alpha, not the second button. Sorry, guys, alpha, and then from there you're going to type F2. So I typed in my 8. Now I'm going to hit alpha F2, and combinations, NCR, is number 8 in your calculator. So I would type that in, and then I would put the 3 in after that, and then go ahead and hit the enter button. So my calculator is showing me 8C3. It looks just like this does right here, and I ended up with 56 possible ways that could work out. Now again, nobody cares, but this would be 8 factorial over R factorial, which is 3, and then 8 minus 3 factorial. So on the top, that's 8 times 7 times 6 times 5 times blah, blah, blah. Here, we get a 3 times 2 times 1 for the 3 factorial times 8 minus 3 is 5. 5, blah, 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 blah. So this 5 times blah, blah, blah cancels with that 5 times blah, blah, blah. And here's something else cool. 3 times 2 times 1 is 6, which just cancels with this 6 right here. And all that leaves us with is 8 times 7, which sure enough is equal to 56. So you could do this stuff without a calculator, but relax, we won't really make you do it. All right, my next example is probably my favorite case of combinations as opposed to permutations. How many different 2-topping pizzas can you make if there are 11 available toppings? So if you think about what are the most common toppings that people get on pizzas, pepperoni, sausage, some people are healthy and they get vegetables on there, green peppers, onions, jalapenos, mushrooms, stuff like that. So what's going to happen? There's 11 available toppings. You're going to pick 2 of them. So let's say you call up to your favorite pizza place and you order a pizza with pepperoni and anchovies on it. So that sounds good. All right, so 2 toppings, pepperoni and anchovies. Then the person right after you calls up and they order a pizza with anchovies and pepperoni. They changed the order here. You said pepperoni and then anchovies right there. All right. And the person after you said, nope, I want anchovies and then I want pepperoni. Guys, is that a different pizza or not? No, it's the exact same pizza. The order in which you put 2 toppings on there isn't going to matter at all. So this is a combination problem. And from a pool of 11 available toppings, we're going to choose 2 of them. So I'm going to go to my calculator, type in 11 first, and then again, alpha, F2, 8, that's my combination button, and then type in a 2, and I ended up with 55 different ways then, guys, that we could come up then with those options right over there. Okay, all right, so 55 ways of doing that. And then last problem right here, if you're going to get into probability here, guys, later on in this chapter, which we are, you got to know something about playing poker, or at least a little bit about decks of cards. So a standard 52 card deck, everybody, hopefully you've all played cards before, right? There are cards there that are ace through 10, and then there's jacks, queens, and kings in each suit, and then in each suit, there's 4 suits in each deck, so you've got hearts and diamonds and clubs and spades. So in poker, you are normally dealt 5 cards at the beginning of your hand, and then depending on which particular poker game you're playing, you might do some different things with that. Now, first question, is this a combination or is it a permutation? Well, if you've played any card game before, even something like Uno or Go Fish or Old Maid or something like that, when you get your cards dealt to you, the first thing that almost everybody does is they reorder their cards so that, for example, in Uno, all of the blue cards are next to each other and then all of the yellow cards and so on and so forth. So the order in which you're dealt those cards really doesn't matter because you can just reshuffle them in your hand. All right. So the order doesn't matter. That means this is a combination problem. And out of a candidate pool right here of 52 cards, that would be our N value, you are going to be dealt 5 of them. That's going to be your R value right here. And the order in which you're dealt those cards doesn't matter. That's why this is a combination. So I'm going to go to the calculator and type in 52, alpha, F2, 8, and then type in 5 at the end of all that, and whew, we get a big number here, guys. You are going to have here 2,598,960 for the total number of possible hands that could be dealt to you when you get 5 cards out of a 52-card deck. So when we start doing probability with card games and poker later on here, guys, this number becomes really, really important. This is going to be the total number of ways you could receive 5 cards there. And then you get into the concept of why in poker one hand is better than another. Why does a straight beat a full house? It has to do with probability and the idea that a full house is more likely to occur, which makes a straight more rare and therefore more valuable. And it's the same reasoning then for why a flush beats a straight and so on and so forth. But I don't want to get ahead of myself right now. All right, guys, that is everything we have from section 11.1. So let's give that homework a try. Good luck, and let us know when you guys have some questions.